All right. Welcome everyone. So today I'm going to talk about chapter 6 in the Goals von Neumann algebra lecture notes. So this is going to be part section 6.1 and part section 6.2. I'll kind of bounce back and forth between the two, mainly focusing on 6.2, but I'll try and put numbers for, lemmas and theorems and stuff that I write down so that you can look at the proofs in more detail as you need to. So the sort of general focus of my lecture is we're going to study an inclusion of two one factors, say n inside of m. And okay, so I'm using the terminology two one factor. By this, I just mean that it's a von Neumann algebra that's a factor, and it has a faithful normal tracial state. By the stuff in section 5, that's equivalent to saying that along with it being infinite dimensional is equivalent to being a two one factor. So we want to study these inclusions, and the idea is that, one way to try and better understand this top level of von Neumann algebra M is maybe by understanding all of its subalgebras N. And in particular, what we're going to associate to such an inclusion is a number called the index, which will be done like this. So this will give us some like numerical invariant associated to these inclusions. And so what's the value of such an index? Well, on the one hand, this kind of stratifies all the various subalgebras. You can kind of organize your study into subalgebras of different levels, different indices. And then also the structural properties of subalgebras with finite index tend to lift to the over algebra M. So it could be that you could study M effectively or kind of discern structural properties of it by understanding structural properties of its subalgebras, provided this index is some finite number. So let's talk about how you define this number, and I should say this is of course motivated by the notion of index in groups. So that's going to be my starting point. I'll work an example to kind of bring us to a reasonable definition of this index for the one coming from groups. So in my example, I'm going to fix a pair of groups, H and G. We'll assume they're discrete groups. You can assume they're countable if you want, but we don't really need them. And let's assume that their index is some number d. So first of all, can somebody remind us what index means in the case of groups? What is this quantity g inside of g colon h?
Like the number of cosets.
Yeah, exactly. Thanks, Otto. So this is the number of cosets in G mod H. It's also like the cardinality of the quotient. So let's fix coset representatives. We'll use 1 for the trivial coset, and then say G2 up to GD. And this gives us then a nice partition of G into these various perturbations of the subgroup H. So this is kind of a naive way to think about the index. It's just viewing this as a partition of sets. But actually, this is kind of enough for what we'll do. This partition of G into these disjoint subsets induces, on the level of the Hilbert space, little L2 of G. We then get an orthogonal decomposition of L2 of G into these various subspaces. Okay, so on the level of this Hilbert space, the index is somehow being remembered as like the number of ways to decompose this Hilbert space into subspaces. And we can make this a bit firmer by seeing how these subspaces are related to each other. So I'm going to let E, this is going to be a bounded operator on little L2 of G. This is going to be the projection onto, let's say, this first subspace, L2 of H. And then for any G in G, let's observe what happens when I conjugate this projection by lambda G coming from the left regular representation of my group. So we know a basis for little L2 of G is things of the form delta sub X for X a group element. And the way the left regular representation acts is just by multiplying the index X. So at first lambda G star will kick the delta over to G inverse X. And then what is E going to do? Well, it's the projection onto L2 of H. So if this belongs to L2 of H, it'll leave it alone. Otherwise, it'll kill it. And when this belongs to L2 of H, if and only if G inverse X is in H. So E is either going to give this thing, send this thing to 0 or itself. And we'll record that as, say, the indicator function on H of G inverse of X. And then lambda G acting on that delta will kick it back to delta of X. And I'm going to also rewrite this indicator function, G inverse X living in H. That's the same thing as X living in GH, just by multiplying by G on the left. So at the end of the day, what did this operator do? It sent delta X back to itself, provided X belonged to this translation of H, and otherwise gave it, otherwise sent it to 0. So what this tells us is that this conjugation of E, this is the projection onto the subspace little L2 of GH. Okay. So in particular, we can apply that for G ranging over my various coset representatives. And I can take the projection onto this first subspace and turn it into projections on these other subspaces by just conjugating it by elements from my left regular representation. And moreover, since these subspaces are all orthogonal and joined together to give me all of L2 of G, the projections onto them will sum up to 1. So consequently, we get that 1 is equal to E plus lambda G1, E lambda G, oh, G2. So let's call the next one. G2 star up to lambda GD, lambda GD star. Okay. Any questions up to this point? All right, so we're tracking our index. It started off as just a number, and now we're saying, okay, the index is like how many projections we got in this partition of the identity. And moreover, these projections are all related to each other. They're in fact, they're Murray von Neumann equivalent to each other, conjugations of one another. But now to turn this into like a number that we can kind of extract from the von Neumann algebra structure, I have to take a bit of a leap of faith. I'm going to make an assumption here. I'm going to assume that the von Neumann algebra, I'll call it M, this is going to be the von Neumann algebra generated by this projection E, and I want all of my lambda G, so everything in the group von Neumann algebra. I'm going to assume that this von Neumann algebra has a faithful normal tracial state. Okay, and a priori, there's no reason to expect this to be true, but we'll see in a bit that this actually is a reasonable assumption. Call this tracial state tau. Then from the above, what we can deduce is, well, if I apply tau to this equation, then on the one hand, tau will send 1 to 1. And on the other hand, for the right-hand side, I can split it over the sum. And using the fact that it's tracial means, well, then I can take this copy of lambda G2 and move it to the back, and then cancel it with this lambda G2 star. And I can do that for each term to reduce it just to tau of E. And well, how many terms were there? There was D of them, exactly the index of G inside of H, times tau of E. So hence, in this case, our index for G inside of H, solving for it in this equation, we can write as 1 over tau of E, where tau is this trace that we're assuming exists on this von Neumann algebra, and E was this special projection onto this particular subspace. Okay. So that's a very von Neumann algebraic way to write the index, and this is going to be how we'll exactly generalize this to more general von Neumann algebras. Okay. So any questions on that example before I now give you some more general definitions? Okay. So let M be a 2-1 factor with unique tracial state tau. And for a unidal von Neumann subalgebra, n inside of M, we'll let En, so it's going to be a bounded operator on L2 of M tau. So remember, this notation is for the GNS Hilbert space associated with the state. I believe Aldo talked about this yesterday. This is the standard Hilbert space for M. So En is going to be an operator on that. It's going to be a projection. We wanted to play the role of the projection E in my example. So it's going to be a projection onto the subspace associated to the subalgebra. So it's onto L2N, the GNS Hilbert space associated to the restriction of tau to N, which we view as a subspace of L2M tau. Okay. If you want, this is just right the closure of N under the norm induced by tau. So that gives you some projection. Then I'll write bracket M En bracket to mean the von Neumann algebra generated by M in this projection. This notation is supposed to be kind of reminiscent of group theory notation, where like stuff in the brackets, you're saying the group generated by this. So I mean the von Neumann algebra generated by all this stuff. This is called the basic construction. For N inside of M. Okay. So this was the thing in the previous example that we had to assume admitted some faithful normal tracial state, and in which case then we could define an index for it. So let's first try and understand kind of how reasonable it is to assert that this thing has a faithful normal tracial state. So here's the lemma. This is lemma 621 in the notes. And it gives us another way to think about this von Neumann algebra, this basic construction. So let J be the canonical commutation operator on L2M tau. So this is the operator that sent x hat to x hat star. And in the previous section, what Aldo was talking about yesterday, what's special about this operator is that if you look at JMJ, then that's just exactly the commutant of M. So what ends up happening in our case is that this basic construction is the commutant of JNJ. And then consequently, this thing is a factor of type T, for T either being 1, 2, or 3 in our type decomposition, if and only if N is a factor of type T. So let me elaborate a little bit more on this. I want to draw a picture for this, which is also appears in the notes. So here's B of L2 M tau at the top of the diagram. Down below, there's a copy of the scalars. Here's M, N, sitting inside of each other. And then over here, we have JMJ, which is M prime. Then over here, we have JNJ. So, and then I'm going to add two algebras to this. So I want to add algebras so that when I want there to be symmetries to this diagram so that when I pass through the center of the diagram, I get the commutant. So for example, these two are commutants of each other because the line connecting them passes through the center. These two are commutants. So over here, I should put the commutant of N. And that indeed contains the commutant of M because commutants reverse the orders of inclusions. And so then similarly, I should put over here J and J prime. And that turns out to be the same thing as J n prime J. So there's two symmetries going on here. One is that passing through the center is the same thing as taking the commutant, and then reflecting over the vertical central line is conjugating by J. And the lemma is saying that this basic construction is exactly this guy up here. So it's indeed some algebra that contains M. It's larger than this thing. And the surprising part is that, you know, from how this diagram is constructed, it's clear that this thing should be some bigger algebra than M. What's surprising is that all you needed to add was this single projection in order to fill this thing out. But the details of that are in this lemma 6.21. This last statement, though, is just really a statement about commutants. I forget if this actually appears in the notes in chapter 4, but it's a fact that whenever a von Neumann algebra has a particular type, then its commutant will necessarily have that same type. And so because these are related by commutants, if this has type T, then this thing will have type T, and this conjugating by J doesn't really change the type at all. So that's how you can end up asserting that this thing and this thing have to have the same type. And likewise, the factoriality of a von Neumann algebra is equivalent to the factoriality of its commutant. So if you accept this lemma, then what this tells us that if n is say a type 2-1 factor, then the lemma implies that this basic construction is a type 2 factor. Now, it's not true that the commutant of a 2-1 factor will also be 2-1. You only get this to hold on the level of these three main types. But we can at least assert that this thing is type 2 because this one is type 2. And then from our subtype decomposition, well, that means that this type 2 factor is either a type 2-1 or type 2 infinity. It's either a type 2-1 factor or a type 2 infinity factor. And in particular, it will have a finite, a faithful normal tracial state precisely in the former situation. has a faithful normal tracial state if and only if it is type 2-1. Okay. So we can then go on to make our definition for this index. The index of an inclusion inside M of type 2-1 factors. Drag this to a new page. So my writing app has frozen. Let's see if we can recover. And let me disconnect real quick and reshare. Give me a minute. Oops. Okay. All right. Sorry about that. So we have an inclusion of 2-1 factors. The index, 2-1 factors, defined B. So motivated by our example of groups, it'll be 1 over tau En if the basic construction is type 2-1 with trace tau. And then in the other case, we'll just set it to be plus infinity. Okay. And that seems a little ad hoc at the moment. We're just kind of saying, well, we don't know how to do it in that case, so let's just set it to be something bad. But this is better motivated than you might think. Actually, this still agrees with what happens in the group case, but I won't have time to go into that. So great. So now we have this notion of index, which is supposed to be modeled after the group case. Let's see some examples of this. So let's start with an easy inclusion, M sitting inside of itself. Then we have this projection onto the subspace L2 of M. Well, what is that projection in this case? By definition, it was the projection onto the closure of the subalgebra under this 2 norm, thought of as a subspace of L2 M tau. Well, what is this? Okay. Well, this is everything. So the projection onto the whole subspace is 1. Are people confused by that? Or what's the hang up here? Okay. Not sure what to do with that. But so if EM is just the identity, then the von Neumann algebra generated by M in this projection, well, 1's already in M, so the basic construction in this case is just M itself. And M has its own tracial state. And so the formula for the index in this case gives us 1 over tau of 1, which is just 1. So the index of M inside of itself is 1. And in fact, for N inside of M, you get that N is equal to M if and only if the index is 1. Okay. For a second example, we'll fix a pair of groups again. Since I've restricted everything to 2 1-factors, I want to make sure that the group von Neumann algebras for these give me 2 1-factors. I do that by assuming that they're ICC groups. And we saw already in the example we worked out that the index for the inclusion of groups was given by 1 over tau of that projection E. But that projection E is exactly the projection associated to the subalgebra LH. So this ends up being the same as the index for the inclusion of the von Neumann algebras, L of H inside of L of G. Now, I haven't told you what the basic construction is in this case, but and I won't in general, but I can tell you what it is for a special case. So if G is abelian, and we think of it as a discrete group, then it has a dual group with compact dual G hat. Then the basic construction in this case is isomorphic to a cross product where H perp, these are the elements in the dual. The dual here are homomorphisms from G into the torus. So these are the subset of homomorphisms that when you restrict them to H, they're trivial. And this action of G hat on L of G is given by this. So it just returns lambda of G to itself, but scaled by some, this is some modulus 1 element. So that's what the basic construction is in that case. And well, we don't have general cross products discussed in the von Neumann algebra notes, but I think we'll go into a bit more detail in the C-star notes. But I'm happy to tell you more about this construction afterwards. Another example is you can take a von Neumann algebra N and then consider the, say, D by D matrices with entries in N. And N sits inside of there. In particular, an element X maps inside of this bigger algebra as the diagonal matrix with all X's on the diagonal. That's the inclusion I'm referring to here. And if N is a factor, then this will be a 2 1-factor. I mean, actually, this is really just isomorphic to the tensor product of N with the D by D matrices. And the index for this inclusion is simply D squared. And the basic construction is isomorphic to the D squared by D squared matrices over N. So there's some exercises in chapter 6 where you work through and show that. And then I'm going to skip an example, but let me mention, so far all these examples have given you indices that are integers, but non-integer indices can occur. And the way you do this is if you take a projection P in the relative commutant of n, so P is a projection at M that happens to commute with the subalgebra n, then there's a formula for these corners, for the index for these corners. So because P commutes with n, we only have to compress on one side. But the index for this corner of M over this corner of n ends up being the original index times, so tau sub m is the trace on M. You apply that to P, and then n prime will have a trace, and you apply that to P. And since projections can have traces in a 2-1 factor, this could be any number between 0 and 1. You can use this to in order to get an inclusion where this index is not an integer. So it's not exactly a concrete example, but this is how to easily construct examples with non-integer indices. Okay. So by definition, the index for an inclusion of 2-1 factors is valued in the interval from 1 to plus infinity. We saw an example of where it was 1, and it takes in a value of plus infinity whenever the basic construction is not a 2-1 factor. And so then a natural question is like, what's the real range for this index? Maybe it depends on this algebra M, like for a fixed M, as you vary n, what are the values this thing can take? And are there any values that it can't take? Well, this is perhaps the main reason why people are so interested in this notion of index is the following theorem. This is due to von Jones, 1983. So for 2-1 factors, n inside of M, the actual codomain for the range, or for the index, is the following. So it belongs to, I'll put the not surprising part at the end. So it can take any value from 4 to plus infinity, but between 1 and 4, it can only take the following values. 4 cosine squared pi over n for any n bigger than 3. And then as n gets larger and larger, you're getting closer to cosine of 0. So that brings you close to 4. So the values kind of get dense as you go up to 4. But the shocking thing is that there's this discrete part of the range. So no pair of 2-1 factors can ever give you anything outside of this in the interval from 1 to 4. And this was extremely surprising at the time. Given how kind of continuous the trace is on a 2-1 factor, everyone expected that it should be the case that this index can give you anything between 1 and infinity. And the fact that that's not true, that it has this discrete part, this is ultimately one of the reasons why von Jones received the Fields Medal. And it has to do with kind of a deep connection to knot theory. These numbers, these kind of mysterious numbers, are kind of roots of knot polynomials, and so that ends up manifesting in this proof of this. And I should also say that for M is R, this hyperfinite 2-1 factor, that was constructed in a previous lecture, infinite tensor product of 2 by 2 matrices, all values above are attained. And we also now know that this is true when you let this be the LF infinity. But for other von Neumann algebras, the range of this thing is kind of hard to, well, it's its own problem. Okay, so I've got about 25 minutes left. So I've got a few more things to talk about here, but this would be a good point to pause for questions if there are any. All right.
Sorry, I was gonna ask.
Yeah.
So, is this like kind of indirectly saying something about what the values of those like of tau of a projection can take?
It's not necessarily limiting what the output of the trace is, because for any 2-1 factor, the output of the trace, the image of the trace on its set of projections will always be a full interval from 0 to 1.
Okay.
What this is saying is that, so for subalgebras of index 4 or higher, then these are kind of like, this is some continuous business, and you can get anything between. But it's saying that there's some restrictions suddenly once you go to small index subfactors. And one way to think about this is kind of putting a limitation on how you can embed certain subfactors inside of M. You should think of small index as being like the subalgebra is kind of large, right? In the case of groups, if we have a small index group, then we're sort of saying that that subgroup is a big subgroup. So this is saying that the large subalgebras of a 2-1 factor are constrained in kind of a mysterious way.
Okay. Thank you.
I should also mention that, like, in this case, when M is equal to the hyperfinite 2-1 factor, then all of its 2-1 subfactors will also be isomorphic to R, but they won't necessarily be the same copy of R. So you'll be embedding one copy of R into itself in some kind of strange way. And this is saying that there's limitations on how you can do that embedding. Other questions? Okay. So let's suppose that we're in the case where our index is finite. Then by definition of the index, that means our basic construction is a 2-1 factor. So we can consider then M sitting inside of the basic construction. And this is another inclusion of 2-1 factors. So we can construct the same objects for this inclusion as for the original inclusion. We can do like a basic construction for this inclusion, and we can also ask what the index is for this inclusion. For the index, it turns out to not be so interesting, or at least not be something new. Theorem 624 tells us that the index for this new inclusion, basic construction over M, is actually the same as the original index. So the index question kind of immediately stabilizes. You're not going to get new indices by kind of iterating this process. But the basic construction, I mean, this is a strictly larger von Neumann algebra than M, provided this index is strictly bigger than 1. As long as this is strictly bigger than 1, M is a strict inclusion inside of the basic construction. So we have actually constructed a larger algebra. And so we could then iterate and construct an even bigger algebra. So iterating the basic construction gives, well, using our notation, it would be this. The von Neumann algebra generated by the basic construction and the projection onto this copy of M. So let's say we do this over and over again. We have M sitting inside of N, sitting inside of the first basic construction, sitting inside of this thing, and then so on. Just so that the notation doesn't get so onerous, let's relabel these. I'll call this one M0, this one M1, this one M2, M3, and so on. So first of all, this series of algebras, this increasing sequence of algebras is called the Jones tower for the inclusion. Increasing sequence M0 inside M1, inside M2. It's called the Jones tower for N inside of M. And you can extract some interesting data from this. I need to state a couple of facts, though, in order to make this explicit. So the first fact is that if you have N inside of P inside of M, then the index for the largest algebra over the smallest algebra is the same as the index of the largest algebra over the middle algebra times the index for the middle algebra over the smallest algebra. So the index is multiplicative in this way. This is an exercise in the notes, exercise 611. It uses an alternate definition of the index to prove it, but this is what you would expect, especially after modeling things after groups. The index for groups behaves in the same way. And then the second fact is that when an index is finite, this implies that the relative commutant, the things in M that commute with N, is actually a finite dimensional algebra. And this we actually prove in the notes. This is proposition 641. So it's a finite dimensional von Neumann algebra, and those are just some direct sum of matrix algebras. Okay. So now, if I consider the Jones tower for a Jones tower Mj, j greater than equal 0, for an inclusion N inside M, say with index equal to lambda, then I can use the first fact to say what the index of, let's say, Mj plus k is over Mj. I can write this as a product of sort of intermediate indices. And if I flash back to previous page, remember that the index for the new inclusion that we generated was the original index. And so as I iterate this basic construction over and over again, every one of these like step one inclusions are all going to have the same original index. So each one of these factors here is equal to lambda. So at the end of the day, you just get lambda to the k for how many steps there were, how many factors there were. And in particular, this is finite. So even if I go very far up the tower and k is some massive number, this inclusion of mj inside of mj plus 1 is still finite index, and therefore by fact 2, it's finite dimensional. Okay. So I'll define one last object here. N and M be inclusion of two one factors with Jones tower Mj, j greater than 0. The standard invariant for n inside of M is the collection of finite dimensional algebras given by the following. So there's going to be two levels to this. The top level will be looking at the relative commutant of M0, which was our original algebra N, inside of all of the higher algebras. And of course, this first one is just equal to the complex numbers because N was a factor. And then the second level, I'll look at the relative commutants of M1. And then I have conclusions like this. Because it's easier to commute with the smaller algebra than it is the bigger algebra. And then this level is also C. Okay, so I get a bunch of finite dimensional algebras all sitting inside of each other. Here's the complex numbers, then there's this thing sitting inside this, and then I have this kind of ladder of inclusions. And this turns out to carry a significant amount of information about the inclusion. It doesn't completely determine the inclusion N inside of M. There could be, let me state that explicitly. So for N tilde inside of M tilde, one can have the same standard invariant as N inside of M without this without these pairs being isomorphic to each other. But it still does tell you an awful lot about this inclusion. And this is a very rich object because, I mean, there's entire books written about these kinds of towers of algebras. We're taking finite dimensional algebras and embedding them inside of one another. And the way that you kind of codify these things is by Bradley diagrams. This is very important in C-star algebras for constructing like car algebras and other examples like this. So this can have a very interesting structure and it can have a lot of variation in it. And then another perspective that makes this interesting is that there's a way to encode this. This can be encoded via a graphical calculus. And by this, I mean these various algebras and importantly, their inclusions, the way they're sitting inside one another. This can be encoded via graphical calculus known as planar algebras. Okay. And planar algebras are, I mean, in one sense, they're kind of like combinatorial linear algebra. And these standard invariants just give you one example. But we also know exactly what kind of planar algebras come from standard invariants. So there's a nice dialogue between subfactor theory and planar algebras. And this is the bridge that ultimately connects subfactor theory to things like category theory and higher category theory. So this is just kind of the initial gateway into subfactor theory and kind of where the modern theory is. But okay, I will stop there. Any questions?
So I like the different types of visualizations that there are for these subfactors. My immediate question is something like, if you have this sort of graphical calculus being invariant, I guess, would you have the Bratley diagrams being the same as well? Is that something that's preserved?
Yeah, the standard invariant can be I think the term is fully encoded by the Bradley diagram. Because at the end of the day, we're just asserting, okay, this is some finite dimensional algebra, and we're embedding into that. And there's some Bradley diagram for that, which should let you fully recover what this inclusion is. Now, you're not going to be able to recover like the individual algebras M0 and M1 from this, but at the very least, these finite dimensional subalgebras you will be able to. And so, I mean, is your question about like translating from the Bradley diagrams to the planar algebras?
Yes, exactly. So like from what I understood, I might be wrong, but you're saying that, okay, so we can represent this finite dimensional objects tower as a Bratley diagram, but also something in the graphical calculus?
Mm-hmm. So that I'm not entirely sure about. Certainly, I think that the Bradley diagram should determine a planar algebra. Well, okay, I need to be careful here. The planar algebra has a bit more structure that maybe is not fully encoded in the Bradley diagram. But so, okay, yeah, I'm not an expert in this part of it, but I think what I would say is that from the planar algebra, you should be able to recover the Bradley diagram, but that might leave a little bit of the data from the planar algebra on the table.
Okay, okay, thank you.
Other questions?